Okay, in this video I want to just spend a little bit of time strategizing about when we would calculate flux as a surface integral. So that of course is just the double integral across S of f dotted with n ds, versus when we would use the divergence theorem to calculate it as a triple integral, the triple integral over the enclosed region of the divergence of v dv. Okay. And in some of these cases we may have options, and in other cases one of these choices might be completely wrong. Okay? And I just want to talk about how to recognize that. Okay? So my first surface is the portion of the plane x plus y plus 3z equals 5 that lies in octant 1. Yes? No. Okay? That portion of the plane isn't the boundary of anything. It doesn't fully enclose anything. If I were to take a look at what that looks like, I could say, okay, my x-intercept's going to be at 5, my y-intercept's going to be at 5, my z-intercept would be at 5/3. I'm looking just at this triangular piece of plane. Okay. So just a triangular piece of plane doesn't enclose any finite solid. So here, this is not a boundary of a solid. So I can't use the divergence theorem if I have a surface that isn't the boundary of a solid. Okay. Now, compare that to surface number 2, the boundary of the tetrahedron that's bounded by the coordinate planes and this fourth plane, x plus y plus 3z equals 5. Now I'm saying my surface is actually 4 surfaces. It's the boundary of the region enclosed here. So it would be this portion of the plane together with this triangular region in the yz plane, this triangular region in the xy plane, and this triangular region in the xz plane. Now, if I were to do that as a surface integral, that would be 4 surface integrals. And while I think surface integrals are fun, I'm going to put a frowny face there. That's an awful lot of work. I'm going to try this one using the divergence theorem because it would be 1 triple integral instead of 4 surface integrals. Okay. All right. My third example. I'm going to say we have the boundary of E, which is the region inside the cone, z equals x squared plus y squared, and below z equals 4. Okay. So my surface would be the cone together with a disk that's capping it off, because I said it was the boundary of this region. So I would have a portion of a cone and a disk in the plane z equals 4. So that would be 2 surface integrals that I would have to do. And again, much as I love surface integrals, that's going to be an awful lot of work. I would probably try using the divergence theorem because it would be 1 triple integral over that enclosed region. Compare that though to this, which is just the portion of the cone below z equals 4 with no cap on top. That's not the boundary of a region. So here I would probably do that one as a surface integral. If I wanted to do it as using the divergence theorem, I could, but I'd have to adjust, because I'd have to say we could take the triple integral over E of the divergence of f dv, but that would actually be the integral over the cone plus the integral over the disk. So I would have to then subtract the double integral over that disk in the plane z equals 4 of f dotted with n ds. So instead of doing 1 surface integral here, I would have to do 1 triple integral, 1 surface integral, and subtract them in order to be able to use the divergence theorem. In general, I think it's likely to be simpler to just do 1 surface integral, so that's what I would probably do. But every once in a while, I'll see people opt for something like this, and that's simply because this surface integral is usually pretty nice. Because if I'm talking about the disk that puts a cap on this, well, it's a very simple region and it has a constant normal vector. The normal vector would be pointing just straight up so that it's pointing away from the enclosed solid, and that tends to make this a pretty simple surface integral. So this is a viable option. Wanted to just show that to you, but I can't just do a triple integral if my surface is not the boundary of some region. Okay. So that's really crucial. Not all flux integrals can be done using the divergence theorem. Divergence theorem only applies if you have the boundary of a finite solid. Okay. So then you can use that, and as a general rule, if I do have the boundary of a finite solid, but that gives me multiple surface integrals, then I tend to think that the divergence theorem is going to be a nice shortcut. If I have just a single surface integral, it's generally speaking not going to be the boundary of a finite solid. Just about the only thing we've seen where we can have just a single surface that's the boundary of a finite solid would be a sphere. Technically, we could have an ellipsoid as well, but you're not going to see any examples of that in the text because that would require us to use flux integrals and divergence theorem and a change of variables using the Jacobian. And while we've got all of those skills, that's a little bit much when we're just learning the divergence theorem and flux integrals. So those are sort of the things I look for, but be very, very careful not to apply the divergence theorem if you do not have the boundary of a finite solid, but be on the lookout for it when you do have the boundary, and particularly when that boundary is piecewise. Or even in the case of a sphere, I often will find that the triple integral over the solid sphere is faster and simpler to do than actually parametrizing the sphere, because the parametrization, while it's not super complicated, it's tedious, it's long to parameterize the sphere in terms of theta and phi.